In the process of looking at rainfall runoff calculations, we saw how we can, if you have rainfall data, how we can calculate runoff. That's obviously based on availability of rainfall data. There's a couple of challenges there. One is we don't always have rainfall data for a given catchment, and two, we instead usually have discharge. Discharge is in a way easier and more easier to collect in the field. That's one. The other thing that we noted in the last couple of slides of last time was that, okay, we have this rainfall, runoff, all of that calculated. The data available and the calculations we do on that available data doesn't necessarily correspond to the design parameters and design inputs that we need. For a given rainfall, we have runoff, but that runoff is not necessarily what we need to use for design. As we briefly discussed last time and will continue today, there's a likelihood of an event that needs to be considered for design purposes, different designs, different infrastructure, these different standards require different approaches. So that's what we're going to talk about today. And this is under the category of flood frequency analysis. We'll look at that. Now, when we talk about probability and likelihood of an event and risk, these are all tied together. It's not a super clear and straightforward idea or concept. Design is typically based on minimum expected cost. So we want to minimize cost. And this is general, this is not a hydrology. We see this a lot in construction and other type situations, but we are trying to minimize expected costs in situations where failure is not unacceptable. So if failure is acceptable, you don't really need to minimize costs, but usually that's not the case. Usually you want to avoid failure, and then it comes with cost, and we want to minimize that cost. For example, failure of a temporary diversion during construction of hydropower intake, that's one that might be a situation we're dealing with. Sometimes failure is unacceptable. So you cannot take any failure at all. In those cases, typically, we're not going to get into details of this, but this is where you typically don't look at likelihood or probabilities anymore. You want to design for the worst case scenario in a way. And that worst case scenario, kind of the interpretation is what we call a probable maximum precipitation or probable maximum flood, PMP. This is common, for example, in large dams. If you're looking at design of a large dam, in terms of the hydrology side of things, failure of the large dam is not acceptable at all. So you're not going to design it for a given probability. You're going to design it for the probable maximum precipitation and the consequent flood that you might get. This is PMF. Again, we're not going to talk about this one much, but we're going to talk about that likelihood and the probability side of rainfall. The trick and the challenge with probability and risk is that, as I said, is not straightforward. It's not like one simple formula. You plug in inputs and you get output. There's some, there's the perception of risk, and it's different for different people, and that makes it challenging. That's why we have design guidelines and standards, because those are the ones that are going to give everybody an unbiased code and kind of instructions to follow. But just to give you an idea, in terms of the different probabilities that we're looking at, this is just an example for different cause of death for different reasons, all the way from vehicle accidents at the top, going down, we have floods, we have like animal dog attack or something, earthquakes, lightning, and so on. You see obviously the number of death goes down. This is historic data, and as the number goes down, the odds or likelihood or probability goes down as well. So that's what we see in the next columns, right? So we want to do the same thing with floods. We want to do the same thing with that runoff calculation that we did. We want to know, okay, for a given probability, what is the flood that we may see at the POC, and we design for that. So that's the kind of the approach that we're looking at. As I said, the whole idea is based on minimizing cost. And how do we do that? Again, this is not limited to hydrology. This is a bigger picture. But if you look at if C is cost of precautionary action, it costs us C amount of money to prevent whatever failure we're looking at, and L is cost if that failure happens. Then the ratio C to L has to be less than the probability that we want. And that's kind of a decision-making approach that we typically do. Again, very common in kind of construction side of things, but the same idea applies to hydrology. Before we get into kind of applications and theory, a couple of terminology, a couple of things we need to know. First of all, risk. What is risk? So risk is defined as probability of an event. So it's 1 in 100, 1 in 1,000, whatever it is, times the consequence. So if this event happens, what are the consequences? And it could be different things. It could be monetary, that amount of damage in dollar amount, let's say, or death, or combination, or social impact, or environmental, and a lot of other things. So that's a big category. So that's what risk is. What we need to always keep in mind is that I'm going to say it's important, is that we have to sum over all consequences. As I said, the consequence category is a big one. We can't be picky and pick one and leave the ones others, leave some of them out. It should be all of them. And yeah, some consequences might be lower in, let's say, importance, but they're still there. So they have to be counted and included. And how do you do that? It's based on expected value of damage. So if this failure occurs, how much do we expect to see damage? Again, damage is not just monetary, but just to keep it simple. And for design purposes, we do the cost benefit analysis, which we're not going to do here, but we basically look at the cost versus benefit, and as we said, that's C to L reference. Just keep in mind this is for cases where failure to some extent is acceptable, meaning that we know we cannot entirely avoid failure, and it's acceptable. It's not okay. We have to deal with it, but we deal with that. Again, as I said, in some cases, like a large dam or large infrastructure, failure is not even acceptable. So we don't really do this. We look for the worst case scenario. Okay, so let's continue this. Now we have the idea of probability, uncertainty, and risk. As I said, the probability of an event that we use for design usually comes from guidelines. So I'm going to write it down here. In practice, again, just to make sure that we don't have that biased risk perception that everybody might have, and it might be different from others. So to avoid that, we have guidelines. So in practice, we refer to standards and guidelines. Just to give you an example, for example, for dams and so on, we use, let's say, for example, CDA, Canadian Dam Association. What they do is they say, okay, if you're looking at this size of a dam, you should design for this probability and so on. So Canadian Dam Association. This is just one example. There's obviously in different disciplines, different areas, they have there are other associations, but this is just one example. Some other examples, just to give you an idea of what we're looking at. For example, let's say we're doing a flood protection. So we know there's going to be a flood. We want to protect the infrastructure against damage due to this flood. So flood protection. Let's say it's a residential housing. For residential housing, if we're looking at a major bridge, so you have a bridge, we have a road crossing, a bridge, which is on a major highway or major road. Typically, the probability, I'm going to use TR, we're going to look at it later, but is a 200-year event. So that's just an example. Typically, we write it as 1 to 200. So it's 1 in 100, 1 in 200 event. For roads, again, depends on how, is it a major road, a highway, or a relatively small road, and so on. But typically 100 years or something like that, or higher, typically for major roads. Minor drainage. So you have a relatively small catchment, relatively small area, and relatively small flow, and you're designing like a stormwater collection system and gutter system. They're typically designed for 100-year event. Yeah, somebody's asking about TR. We're gonna look at that. That's a return frequency. We're gonna look at it in the next slide. I'm gonna define that. But for now, we're just giving you some numbers to at least get a sense. And if failure, as we said, if failure is not acceptable at all, is not acceptable, typically large infrastructure where there's major risk and consequence, including potential loss of life and so on. I'm going to say, for example, large dams. We don't really say, okay, 100 years or 200 or something. We actually say we should look at whatever can potentially ever happen. So infinite, which is equivalent to what we said, the probable maximum flood. What is the largest flood that could ever happen? We should design for that because we don't want it to fail, right? So keep this in mind. We're going to come back to these numbers and actually do some calculations. But for now, that's just to give you a picture. Now let's go back to hydrology. So what do we do in hydrology? So as we saw before, typically we have some historic data. We have rainfall data that's been collected or runoff data, usually one of the two. And we want to do some calculations, get a number for design, the Q peak runoff magnitude that we want to use, right? So there is data from the past. So if we plot it, if we plot whatever data we have, let's say discharge with time, and this is now, this is right now, there's data in the past, right? And we're designing this structure now. So it's going to perform, it's going to be around in future. This is future. So we need to know what is potentially going to happen in future so our structure can handle it in terms of flood or rain or whatnot, right? And the question is, okay, if we have data from the past, is it just going to copy the same pattern and just do this? You know, something like that. Or maybe it might actually start going up, so we have bigger floods. Or who knows, maybe it actually goes down, right? These are the questions that we have to deal with. And the challenge is we have nothing from future. Obviously, we can't see the future. This is why we say hydrology is a stochastic process. Stochastic in a deterministic system, which is the opposite of stochastic, there's no randomness. You have given inputs and they always give you the same output, kind of straightforward. A stochastic means, yeah, it pertains to chance in terms of meaning, but it really means that there are parts of the system, it could be one or more, that have some randomness associated with them. And because of that, forecasting what's going to happen in future is not super clear. How do we deal with that? Instead of saying, oh yeah, okay, it's going to be this magnitude in future, we use statistics. We assign probabilities to each of these events. For example, the three projections that I have on the screen, we could say, oh yeah, that purple one is probably 10% chance that might happen. The green one, 55%. The yellow one, maybe 15%. So we assign probabilities. And that's a background behind why we, in the previous slides, we kept talking about probability. So what happens is we say, okay, I'm gonna sketch this. We might have something like this, okay, which is very kind of normal behavior, what we expected, what was happening in the past, just copies into future, or it might go up or go down, right? So we don't know which one's which. So what we do is, by the way, this is, let's say, time and discharge. What we do is we say, okay, let's assign a probability. So probability to each of these events. And let's say it looks like this. So chances of, it's at the max, chances of the future following that green trend is this much probability. The other ones, something different. For typical normal natural processes, we have the normal distribution, which I'm not going to talk too much about, but if we have that kind of process, in simple words, following what we have seen in the past has the maximum probability into future. So whatever we're seeing is most likely, compared to other scenarios, is most likely to happen in future. That's why it has the max probability, right? Now, the challenge with this is a couple of challenges, but one challenge is typically we don't have a lot of data from the past. Remember we talked about rain gauges and, discharge measurement stations like gauge stations and so on. If we're lucky, if we have a couple of decades of data in most streams, even the major rivers and streams and systems, usually there's not a lot of data. That's the biggest challenge, not having sufficient data. And why is that an issue? Because let's say you're looking at the structure and the lifespan is 100 years, 200 years, or so on. And you don't have that length of data from the past to even project it. Yeah, the vertical means is magnitude or whatever the parameter is, discharge or something in this case. So here's an example. Let's say we have this data, and this is the Lillooet River near Pemberton, but just an example. Let's say we're looking at historic peaks from, what is it, 1914 all the way to 1980 or almost 2000. And we say, oh, okay, it looks like that there's been a large peak somewhere here, right? And we might actually say, this is real data. We might say, oh, okay, so very likely if I'm building a bridge now in year 2000, if I design it for 1800 CMS, which is the largest flow ever in this river, which happened in 1940s or something, I should be okay. That looks like it, right? The challenge is that's not what happened. The data after that actually showed a higher peaks. See the flow, actually larger flows happened here and here and here. Actually, three of them in a decade or so, 2 decades or so. So this is where we kind of had the data before. And that is why we can't just say peak that maximum probability and project it into future. We need probabilities. And this is where this connects to the codes and guidelines. So the codes and guidelines say, okay, if you have a major structure and you're designing a bridge on this river, you have to design it for 200 years, whatever that is. And that number is going to be something bigger than what we saw in the past, something that was here. And that hopefully will capture these three peaks that we have. So stochastic is exactly what we're talking about here. So you have some data from the past, but there's some randomness. We don't know exactly what it's going to do in future. So we can only assign, the best we can do is we can assign probabilities and say, okay, there's this probability of this magnitude. And again, refer to guidelines and see which one you have to use in terms of probability. All right, so let's now define some terms, and then before we actually get into calculations. First of all, we were talking about a parameter, let's say flow, that's the most typical one, flood, discharge, Q, right? There's the first thing that we have is the annual probability of exceedance. So what is this? This is if, for example, you have an annual probability of exceedance of 0.01, what does it mean? It means there is a 1% chance per year, every year, you have a 1% chance for flow to exceed, exceeding certain flow. So first of all, we use capital P, annual probability of exceedance, and that number tells us what are the chances per year for this parameter that we have to exceed a given number. For example, probability exceedance of 1% in this river is 10 CMS. So there's a 1% chance that per year your flow will be more than 10 CMS. Units, in terms of the units for P, units of P is 1 over the year. Okay, so that's what it is. So basically, in simple words, it means what are the chances of, again, flow is the most common one, so let's just stick to flow. What are the chances of flow in this river to be higher than whatever magnitude, 10 CMS, 10,000 CMS, whatever the size is, right? Following this, we also have the idea of non-exceedance. So what is that? That should be straightforward. That's 1 minus P. And for example, in our example, it will be 1 minus 0.01, and it will be 99%. So it means what are the chances of, in this case, 99% chance per year for the flow to not exceed whatever number discharge we're looking at. Okay, so exceedance and non-exceedance, P. Then we have return period. Typically, we use capital T, and it's equal to 1 over P. P is the probability of exceedance, annual probability of exceedance. For example, we had 0.01, right? In this case, if P is 0.01, then T will be 1 over 0.01, or it will be 100 years. So the units for P are years, and sometimes we typically write it as 1 in 100, and we say, okay, this is the 100-year discharge, Q sub 100. So it means a discharge which has a return period of 100. Okay. What is this in terms of the statistics? This is statistical average between occurrences of whatever event we're looking at. In other words, it's a statistical type calculation. It's not again, it's not deterministic. It ties to probability. Okay, so that's what it means. For example, we could interpret this as how many Q100s can occur in a century. So in 100 years, how many Q100s can potentially happen? That probability is 1 over that probability will be the return period. And so far, P is probability of exceedance. What's called axis of the probability graph. I think I answered that question. And return period T is 1 over P. So it's in years, and it's the statistical average of an event like Q100 happening. All right, let's look at the third one, and then this one ties all of them together. Probability of exceedance in 1 year. So what is this? What is this talking about? It is telling us what is the probability of the one in 100 year flood occurring in a period of 100 years. Okay, so the answer to this question will be probability of exceedance in n years. The way we calculate it, the equation is there: 1 minus p raised to n. N is the number of years. Okay, let's calculate this for our example here. Probability of Q100 to occur at least once in 100 years is equal to 1 minus 1% raised to 100. And if you do the calculations, it will be 63%. Okay, so what is it saying? It says chances of a Q100 to occur in 100 years is 63%, to occur at least one. Now, here's the tricky part before we move on to the next concepts. So when we say the return period of discharge is of this particular discharge is 100, 1 in 100, or in 150, 1 in 20, 1 in 200, whatever it is, it does not mean that it's going to happen once in every 100 years. That is something that is sometimes I see people are confused with, even professionals sometimes. So that's just a statistical average between occurrences. That's just like a statistical estimate of this stochastic process. If you want to know exactly how many times, at least how many times we'll have Q100 in 100 years, we can use this equation. In this case, it will be 63%. Now, theoretically, statistically, you can have a 100-year Q100 every year in 1 century. Theoretically, physically, probably not possible. Nature is not going to allow us, or physics and catchment rainfall runoff processes are probably not going to be able to have that to occur. But theoretically and statistically, there's nothing that tells us you cannot have Q100 every year. So keep that in mind. This is very important because it has happened in the past, in the last couple of years, actually, in the last decade or so, a few times happened in Alberta and BC and so on. We had big floods, and everybody was like, not everybody, but some people were saying, oh yeah, okay, this was a Q100, so we're good for the next 100 years. We're not going to get a big flood. And in fact, a couple of years later, we had a huge flood, maybe even bigger than the previous one, or equal, or almost equal, a couple of years later. So this is just a statistical average. It doesn't tell us that it happens once every 100 years or 50 years or whatever the return period is. It's just a statistical number. So keep it in mind. Okay, now before we again come back to this and calculate some probabilities for flood events, a little bit of review of probability. I'm not going to get into too much detail of probability. I'm assuming everybody is familiar, but just very quickly review some concepts. For example, let's start with this. If you have a series of events, let's call them X, and each one has an assigned probability of occurrence of P of X, and if you plot the probability, you have a bunch of points, and if you plot, this could be tossing a coin or floods in a river or whatnot. You get something that looks like this. The shape of this graph could be different. One of the probably most famous one, which actually applies to a lot of natural processes, is what we call the normal distribution or Gaussian distribution or bell curve or different names, but maybe I'll write it here. Normal or Gauss or Gaussian distribution or bell curve or so on. Not the only one, but one of the very common ones. And how is this, how does it look like and what does it have? It has a peak. The peak always occurs at the average, statistical average, let's call it mu, and has a distribution about the average. Now, the properties of this curve or distribution are such that probability of every event is greater than or equal to 0, so we don't have negative probabilities. And if you integrate throughout the entire domain from negative infinity to positive infinity, p of x dx, you get 1. So that's the area under the graph. 1, that's one meaning. Second one, it means among all possible events that could occur, x values, one of them will at least happen. So if you integrate all of them, you're going to get 1. So for sure, 1 will happen or add up to 1. This is typically called the PDF, which stands for probability distribution function. So PDF. Okay, for a given event, so let's say you say, oh, x equals x1, which is here, right? Or x equals a. If you integrate from negative infinity to x equals a, you get the probability of non-exceedance of x equals a because it's to the left. So values which are smaller than a, right? So this is how it ties to what we were talking previously. Now, if you actually continue doing this, and so we still have x here, and for the range, for the values you can have for x in the domain, if you continue integrating from negative infinity, to a integral of px dx, you get a graph that looks like this. And we typically call it capital F of x. So capital F of x equals this. And it's called the CDF, the cumulative density function. Density or distribution, by the way, so different terms, function. So it's basically the cumulative version of P. What does it say? It is equivalent to saying what is the probability of any x that is smaller than or equal to a. That's what capital F of x is, right? So in this case, in the example we have, if we continue this line down here, this will be x equals a, and the number we get will be f of a. So that area up there, this area is f of a, right? So we're integrating p, really, that's what it is. So yeah, hopefully you're familiar, but if not, we don't need too much detail of statistics or probability, but we need to know some simple concepts. Now, how do we describe the distribution function, the PDF? So as we saw, generally in the general form, it looks like this. For any given flow, this could be discharge Q. We have probabilities of P of Q or X, and we have the curve itself that looks like this. Again, simple version. Has an average, statistical average, let's call it X bar, which is exactly at the peak, right? And the way we show the shape of this distribution with X is we can look at each value and look at their distance from the mean. So we could say at xt, okay, we are here. The probability of xt is right here on the graph, and it's located at a distance of this much from the mean, from x bar or mu. And this distance, for simplicity, we typically say, let's say it is a coefficient of kt times standard deviation of the data. So S is a standard deviation. Okay, so let me highlight these terms. This is the mean, statistical mean, and S is standard deviation. So what are we doing here? We have a curvilinear graph, right? But for simplicity, we're going to say, let's just say we have a mean, X bar, and every other point or probabilities about the mean are located at so many S standard deviations from the mean. And that so many, that number, that coefficient that shows up in the front is KT, and it's a function of that number that we're picking, that XT location, right? Obviously, it should be clear that KT depends on, for us, it depends on T, the return period. So let's just go back and replace X with Q and say, okay, what is Q100, Q200, Q10, whatever. So that is our return period. T is our return period. So depending on the return period, that KT will be different. And in simple words, as I said, we are really saying that how many standard deviations or S's away from the mean, away from mean X bar. So this is a kind of a simplified approach to calculate or represent a distribution function PDF in simple words. So let's look at an example. First of all, this is called the method of moments. We're turning that curvilinear function into a linear form, depending on values for KT. This is still non-linear, but the equation itself looks linear. Let's say we're looking at a river, and we looked at the data available, and the standard deviation of the data is 15 cubic meters a second. We just calculate the standard deviation. That should be straightforward. It could, yeah. Somebody's asking, is it just the Z from the Z table in the Z? That's one of the ways. Yes. So in general, it could be depending on the type of distribution that you're using. KT will be different, but yes, that could be one. And then let's say our Q mean, which by the way, also sometimes we write it as Q2. Yeah. An event with a return period of 2 is the mean. So Q2 is, again, we looked at the data and it looks like it's 55, right? So this is for a return period of 2 or a probability of 50%. So it means every year there's a 50% chance for the flow to exceed Q2. And let's say we looked up our guideline and it says, oh, you're designing a major bridge, so you have to design it for 100 years. So your return period will be 100 years, right? And let's say KT is, I'll come back to this, but let's say KT is 2.5. Again, depending on what method we're using, it will be different, but let's say it's 2.5. Then I'm going to say Q100 will be equal to 55 mean plus KT 2.5, K sub T times S 15. And I don't have the number here, but if you do the calculations, it will be your Q 100. Okay, so what are we doing here? So we're actually using available data. What do we do with the available data? We get S and Q2, mean and standard deviation. And then we pick a distribution shape or function or method. Based on that, we get KT for a given return period. Return period typically comes from design guidelines. Depending on what you're designing, that return period is pretty fine. So we have T, we have X bar, we have S. KT comes from the distribution, and then we can calculate that return period that we want. So bottom line, we need two things. We need actually three things. We need available data to get S and Q bar. Then we need to pick a return period, T, and then we need to pick a type of distribution. What is the distribution that we're looking at so that we can get KT, right? So let me summarize these that we just talked about. So we are really express the value of X for a given P or T. You know, we can just convert them easily. P of exceedance as a function of let's call it the distribution. This is telling me distribution tells us how are probabilities distributed for different discharges, right? That's what it means. I'm going to write in brackets K sub T because that's really telling us what the distribution is. And then the other thing is depending on T again or P. These are the same thing really. P is 1 over T. We need to, I'm going to say lookup because it usually comes from tables. Look up KT. So we decide what kind of distribution we want, and we look up KT, and then we go from there. Okay, before we get into applying this to actual data and so on in an example, a couple more things. First of all, the normal distribution is not the only type of distribution that we have. As I said, it's very common, especially for natural processes. Most natural processes follow a normal distribution, but not all. So the shape of the PDF, the distribution, probability distribution function or density function, can have different shapes. One of them is what we call the skewness of the graph. So what does that mean? It means if you remember the normal distribution looks like this, so it's basically symmetrical, goes up and then comes back down. If you have positive skewness, I'm gonna say this is skewness. If you have positive skewness CS, C sub S, is actually skewed to the left. You see that? The black one is to the left of the normal distribution. By the way, let me write it down, normal. If you have negative distribution, it looks like this. So this is where you have a negative CS. So, and obviously normal distribution has a skewness of 0. It's not skewed at all. So CS is 0. So skewness is 1, tells us is the distribution skewed to left or right. The other one is kurtosis, and this one's C sub K, and it is a measure of the peakiness of the distribution. So I again have the normal distribution, looks like this, right? That's normal. So let me write it here. Normal is this red line and has a CK of 0. If we have a positive CK, like the black line we have there, it's narrower and taller, so it's peakier. if we have a negative, if I have a negative CK, it looks like this. So for this one, let me write it here. CK is negative. The kurtosis coefficient is negative. I have the Excel functions here, SQ and curve in Excel actually give you these coefficients for different distributions, but it's always good to know what do they mean? This number, what does it exactly mean? So both of them compare your distribution to the normal distribution. Is it skewed to one side or is it peaky or not? And again, as we said, CS and CK are 0 for normal because these are both actually calculate or are using the normal distribution as reference, really. That's what they're doing. Now, we know that, as we said, most natural processes follow the normal distribution, but not all. Now, people have looked at floods because they're very important for engineering, HLH type studies, and they try to see, okay, what is the shape of a PDF for flood events? And there's a bunch of people have done this, but there's a few famous ones. Probably one of the very famous ones is Gumbel, this guy. And the distribution he came up with is called the Gumbel distribution. He looked at other types of distributions for different events, but the one that he has for floods is EV1. EV stands for extreme value. Extreme value type one. And he noted that for floods, they're not normal distribution. They don't follow the normal distribution. Their PDF has a skewness of 1.14 and a kurtosis coefficient of 2.4. And based on this, he modified or came up with an equation for the distribution. I'm not gonna use that complicated, scary equation, but just know that what it looks like. And what he did, why is it called extreme value type study? Because if you remember our cumulative CDF function, it looks like this. And as you approach larger and larger X values or bigger and bigger floods, you're getting into an area where the events are extreme, like extremely large floods and so on. So this is EV, extreme value type study. That's why it's called the EV, extreme value study. Now, he came up with this equation for P or F, that's easy to convert them, and came up with two new parameters, alpha and beta, and both of them are written on the slide. One is a function of the standard deviation. So instead of actually dealing with the skewness and kurtosis and so on, he simplified the equations, really. That's what they did. And beta is a function of standard deviation and the mean, both of them. So that's this one's also standard deviation. Now, again, one way is to use these relatively complicated equations, but remember the method of moments, much easier. So if you're using the method of moments, you can actually just look up the KT values. So I'm going to highlight this as Gumbel. For a given T or P, as we said, you can pick up the KT values from this table and plug it into your method of moments and actually use the method of moments to get your XT, Q100, Q50, Q200, whatever, right? So it's basically using the X sub T equals X bar plus KT times S. I still need X bar and S. So I need data to calculate those, then pick my T, get KT, and then calculate X sub T for whatever T I want. That's basically what I do. I know this is a little bit of a small sketch, but so basically what we're doing is we're saying for any given X event, curve looks like this, has a mean of X bar, and any number that you're interested in is located at a distance of this much. So this is X sub t, and this distance is kt times s. That's the method of moments, right? Now, Gumbel is not the only distribution. There are other ones. I have a couple of them listed here. I know it's a little bit small, but the first one is normal. That's the actual equation for normal distribution. Second one is EV1 or Gumbel. Sometimes it's just called EV1. And the next one is log Pearson 3, type 3. So Pearson is another person who studied floods and came up with equations. All of these, normal distribution, Gumbel and Pearson, you can also, you have two options. You can apply the data to the data as they are, or to the log of the data. So whenever you see a distribution says log Pearson, log Gumbel, log normal, I don't think we have log Gumbel, but if whenever you see log, it means you do exactly what we talked about, but you apply the approach, the calculations to log of the raw data, not like average of the log of X values becomes X bar, and the standard deviation of log of the data becomes S, and so on. So that's the only difference that we really have to worry about. So yeah, basically we have data, we calculate X bar and S, and pick up T or decide about T, look up KT, plug it in here, and you get X sub T, Q100, let's say, and so on, right? Now, the big question here is, okay, the very first step is to have data. I need data. If I have rainfall data, I don't need to do any of this. I have to convert the rainfall to runoff, and then for any rainfall event, I get one runoff, and then I do the same thing, and that becomes my data. Calculate their mean, their standard deviation, T, KT, and so on, right? But as I said earlier, it's actually more common and more practical to get water level data, gauge stations. That's what they call them. Sometimes called gauge stations. These are stations where different things are measured, but typically water level versus discharge. And these give us historical data. So if I have a catchment and looks like this, and this is the POC, right? And the stream network looks like this, right? I might be very lucky, and I might have a gauge station right here at the POC. That would be amazing because I have data where I want it. And that would be really good. And sometimes it is the case if you're looking at a major bridge on a major crossing, there might be a gauge station right there. But that is not always the case. Sometimes we have data at other locations. You have, for example, you're studying something at the POC, but the gauge data is available here, and then maybe here, and maybe another one here, but not where you want it, right? I'll come back to this and give you a method to deal with these situations too, but that would be a slightly different approach. But typically, they give us data. If you're working in Canada, the Water Survey of Canada, WSC, provides this data. Typically, they have discharge and water level. Those are very common ones. Sometimes they also have other types of data like sediment, sediment loads, and sometimes even water quality type data. Not all, but sometimes, right? And typically they also give you a time series, so you have time and you have data, whatever it is. Let's say discharge. So they give you data with time, right? So you still need to do your statistical analysis to get whatever you need, but the data is available. But there are challenges with this. One is there might not be a long enough historical data. So you have 20 years of data, 30 years of it. If you have 50 or more, that's actually amazing. That's very, being lucky. But it's usually not that long. And also, usually there are gaps in the data because these gauge stations are sometimes they get flooded or they get damaged, or for whatever reason they're not maintained for a while, and then there's no data and so on. But again, that's the best we have anyway, so we have to deal and work with that. So if you're in Canada, WSC is the source. I have the link here. Hopefully the link is still, I think it is, but if it didn't work, just search for WSC and you should be able to get the link. If you're doing work in the US, again, there's a couple of sources, but USGS is a good one. Very similar. They have uh, gauge information, and you can basically pick what you want and you typically download them as text file or something, and then do the analysis you want. So what do we do with this data? So this method that we're looking at is called the graphical method. So what do? We have a bunch of data, we download it, or the client gave us, it's discharged with time, right? And it looks like this. Let's show you just as an example, right? So we have a bunch of data that looks like this. What do we do with this? First of all, I'm going to be using the data. So I'm going to say in the graphical method, I'm using historical flows. And that's typically Q and or variable, right? Okay. How do I turn this data into probabilities and do the calculation? First of all, it's easy to calculate mean and standard deviation, right? That's just one line, one row in Excel or whatever tool you're using. But here's what we do. We arrange the data, all the data you have 10 years, 50 years, whatever it is. Arrange the data in a descending order. So that means pick the biggest one, put the biggest one at the top and the smallest one at the bottom. Descending order. And assign a rank. We call it a rank to each, let's say, row. Okay. What this means is that rank 1 to largest and rank n to the smallest, and you keep going down, right? And then we assign, I'm going to give you an example in a second, and we'll see what this means. Assign what we call a plotting position. This is trying to convert the rank into a probability to each row. And then use this to estimate probability for that row. Probability of exceedance. Or T. P or T, doesn't matter. These are interchangeable. Well, in a way, you can convert them. For each row. And now we have a bunch of flows and their probabilities. That was what we needed. Now we can start plotting our PDF. We're not done yet, but that's the first one. Okay, so let's see what it means. First of all, for the plotting position, there are different methods that are commonly used and relatively easy anyways, but different ones that are available. Weibull is a very common one because it's very easy and it's very common. So that's usually choice number 1. There's other ones, but these two are usually used with Gumbel distribution and median and so on. So, okay, what did we do? We have a bunch of data and we said, okay, I'm going to order them. So I'm going to say I have QIs and the biggest one is up here, Q1, Q2, Q3, Q4, all the way to Qn. So that's my flows from WSC, and I sorted them. Biggest one at the top, smallest one at the bottom. Now I'm going to assign a rank. Rank is just the row number, really. 1, 2, 3, 4, n. And now I'm going to calculate T or P. Doesn't matter. Okay. And this is, again, referring to the table, will be n minus 1, n plus 1 over 1, n plus 2, n plus 1. It's always n plus 1 over m. 2, n plus 1, 3, n plus 1, 4, n plus 1, n. And that would be our T values, return periods. Or P, you could use P, doesn't matter really. I'm using the Weibull method, by the way, here, right? And now what do I have? Now I have a bunch of return periods and their corresponding discharge, QTs. And let's say my data looks like this. Okay, so in here, N is number of points or available data points, usually years. Year 1, year 2, and so on. And M is the rank. As that's the position of that data point in the row in the descending order. So 1 means largest. Let me write it down actually. Okay, now I have the distribution. I have the data, QTs versus Ts. Next step is I'm not done. I need to actually extend this and find the PDF. How does the data actually, distribution of the data look like? So for doing that, I need to look at the extreme event distributions. We looked at Gumbel, right? So we're going to look at extreme extreme value distributions. And there's a bunch of them, as we said. Gumbel is very common, in particular in Canada. We use that a lot. There's typically log Pearson type 3. This is common in the US, usually. You can look at normal. You can look at log normal. And so on. These are the common ones. These 4 are really the most common ones. What do? We have T versus QTs. We just calculate those, right? And we have a bunch of data points. They look like this. And now I'm going to say, okay, let's look at distributions. Look at normal. Normal looks like this. Let's say this is normal. And then I look at Gumbel. Maybe Gumbel looks like that. I'm fitting a distribution to the data. It's just regression, really. And then maybe I have log Pearson, and log Pearson looks like this. Log Pearson 3. Then maybe I also have log normal. And so on. And now I'm going to say, okay, which one fits the data best? Again, when I say Gumbel is most common in Canada because of the characteristics of typical soil and catchment and others, most floods follow that. Not necessarily all, but most of them follow that distribution. So it's always recommended to check all these 4 at the minimum and see which one fits the data the best. And the other question you might have here is that, okay, why do I do this? Why did I not have QTs? Yes, but usually our QT values go all the way to, I don't know, let's say 50 years or 20 years or 50 or whatever, right? So we typically, in fact, if you have 50, that's rare and very lucky. We rarely have more than that. So if I'm looking at the design flow for 100 year or 200 year or 500 year or 1000 year, definitely I don't have data. So I have to use whatever I have, find the best fit, one of these, and kind of extrapolate into whatever that T return period that I have and I'm looking for, whatever that is, right? So that's why we need these regression methods, and we have to basically follow these. Yeah, so that's basically how this continues. I have a summary of this. Nothing new. We just talked about this, but here's what we do. First, we collect the historic data, and that usually comes from whatever sources we have. And we download them and we look at them. We do our ranking and sorting and distribution type steps. If you're doing, by the way, if you're doing log normal type distribution, if you have Q, if you're doing log all the way to Q2, we have to actually take the log right here and do exact same thing, but apply it to log of your data. So nothing different really. Then we have the rank, and then we have the return period T. And we assign M and do this. And now we have T and corresponding QT values. Now we have to pick a distribution. So our data looks like this. And a bunch of distributions that maybe look like this. And I can use whatever method I'm comfortable with to figure out which one fits best, and then use that to extrapolate into future and get the data I want, and use that to for design purposes. I have a really quick example here. It's not really an example, but just to quickly show you a tiny one. So this is what we have. We have a catchment, let's say. Let me switch color. This is what the catchment looks like. This is the POC. And this is the stream network, right? And we have data, and the data is given from, let's say, WSC. We have data year versus discharge. And for different years, for 2015, 2016, 2017, 2018, I'm just making up data. Discharge was 382, then it was 602, then it was, this is the peak annual discharge, the largest flow measured in that day, in that year, cubic meters a second, right? And I want to do a frequency analysis. See, there's a question. Yes, is the largest value Q1. So what do? I'm going to first sort them. So I'm going to say year and then Q. What is the largest one? 2016, 602. Second largest one, 2018, 540. Next one, 2017, 451. And then last one, 2015, 382. Rank, easy. 1, 2, 3, 4. Yeah, we shouldn't really do frequency analysis on only 4 data points. That's not going to be accurate, but for this example, right? T return period is N plus 1 over M. And N is equal to 4. We have 4 years of data. So it will be 4 plus 1 over 1. This would be 5. 4 plus 1 over 2. This will be 2.5. Oops. 4 plus 1 over 3. This will be 1.67. 4 plus 1 over 4. This will be 1.25. Right? So these are the return periods. Now, next, I'm gonna plot my data. I don't actually have actual data, but I'm going to plot these and use Excel or whatever tool you are comfortable with to figure out which distribution fits best, and then use that method of moments. Pick your T, look up KT, and go from there, right? So very quick example. Now, one thing I mentioned before is that let's say this is our catchment. I briefly mentioned this, right? And this is our stream network. Right? And there's a POC right here. That's our POC of the entire catchment, which is great. And we have flow out of this catchment at POC of Q1. Okay, let's say this is a, whatever, WSC gauge. So there's data there. Okay, but now I'm studying and I'm looking at a small catchment, a small bridge crossing, and it's actually up here. That's where the bridge is. And the contributing catchment is this area. And there's no gauge. So I have data in a bigger catchment, but that's downstream, and the bigger catchment, that's not really what I need. So what do we do? Let's say this bigger catchment has an area of A1, and this is smaller catchment, which has no gauge, has an area of A2, and there's no gauge. So what we do in cases like this, and it's very, very common, this is all the time, is that we assume that discharge or runoff is proportional to area of the catchment raised to a number like alpha. And following that, we could say if one catchment is a subcatchment within the next one, the ratio of discharge between the two is equal to the ratio of their area raised to alpha. In BC, again, that manual that I showed you, alpha is estimated to be A or alpha, doesn't matter. I think I used A, so let's keep it consistent. A is approximately equal to 0.75. This is called regional analysis. So you're looking at the region within a catchment and you're transferring data from a bigger catchment to a smaller catchment. As long as the catchment characteristics are similar in terms of land cover, runoff coefficient, slope, relatively, they're not going to be identical, but more or less similar. You can transfer data from one POC to another one only using their area, really, which is again very practical because sadly we don't have gauge stations everywhere that we are studying and have a project. So that would be amazing, but that's not what we have, right? So here's what it is. So in BC we can use that equation, and it's called the regional analysis equation, and it assumes that discharge is equal to a coefficient multiplied by area raised to 75. So what do we do in regional analysis? And you could do it on, it doesn't have to be a sub-catchment. You might have a catchment that looks like this, and another one actually right beside it has a POC here. And you could still do this. You could still use the regional analysis. You could say Q1 to Q2 is equal to A1 to A2 raised to 0.75. The only thing is that we are making a lot of assumptions here. I'm gonna say notes have to be similar catchments. What does it mean, similar? It means topography should be more or less the same, or not the same, similar. What is topography? Elevation, slope, and so on. Obviously, similar climate. You can't take one from a very cold region and use it in a very hot and dry region. Obviously, that's not going to work. Land use, which means the type of soil, type of vegetation should be, again, we keep saying similar. We will never be identical, but similar. If you have any lakes or, those kind of reservoirs on those kind of features, obviously they have to be taken into account. And the biggest one is area. The area should be comparable. You can't use a catchment that is 10,000 times bigger and do a regional analysis. That's just not gonna work. That's not really acceptable. Or it's gonna give you data which is off. So again, very quick example, tiny example here. Let's say I have a bunch of catchments and I did frequency analysis and I calculated their Q200 and catchment. I have 4. I have A, B, C, and D. This one is 155 CMS, 310, 300, and 417. And I have more than 2. So in cases like this, we could do a little bit more accurate. We could say, let's plot area versus Q, in this case, 200, right? And I'll have a bunch of data that look like this. This is A, this is B, this is C, and let's say this is D, right? And then fit a line. This will be Q proportional to area raised to A. And then now that I have this, for any given catchment, like catchment E, I can actually use the graph to get Q200 in catchment E, right? I could be creative and use this for to be a little more accurate. So yeah, we covered a lot of different methods. Some of them we didn't really get into details. I think for those who will study hydrology in more detail, we'll get to that. But this is a nice summary. For catchments which are less than 25, we can use the rational method. If we have data that's less than 5 years, we need to do something. We can't do frequency analysis because 5 years is not much. We need minimum 5 years. We can do unit hydrograph. We didn't talk about it much, but that's the hydrograph from a unit rainfall event. If it's between 25 and 100, see, it says you can still do regional. You shouldn't be doing regional anymore, but you can, sorry, the rational method anymore, but you can do regional. So find the smaller catchments, do the calculations and runoff estimates, and then transfer it to your catchment. If it's bigger than 100, you really have no choice. You only have the regional analysis method to do. These methods, these calculation and kind of steps are not super complicated, but take a fair bit of time. Luckily, there are software packages that actually do this for us. HiFront Plus and HEC SSP. I think I mentioned HEC RAS before. This is another HEC software category from US Army Corps. This one's free, but HiFront Plus is not free. It's not expensive, but there's a demo version. And they do exactly what we talked about. They do the frequency analysis and do the curve fitting. They do all of that for you. And also in terms of catchment and rainfall runoff process simulations and modeling, there are other software like EPA Swim and HEC HMS. Both of them are free and available, and they actually do this type of calculations for us. So if anybody's interested, we're not going to do that in our course, but if anybody interested, you can look up and start using them, and hopefully that will be helpful to you at some point.